Hello, in today's Advanced System Lecture Programming. In this lecture, me, Jörg Thalheim, will talk about unikernels, which are specialized single address space operating systems, and in particular about Unigraph, which is one of implementation of an unikernel. So what are unikernels? They are lightweight application images that not only have the application, but also the operating system bundled to one image. And this whole thing runs as a single kernel in a single process. And yeah, commonly you have different address spaces between kernels and applications, but in unikernels, you only have one. So to make a comparison, you may know how traditional operating systems achieve isolation. So you have like a monolithic kernel, and then you have applications running in this, and one application cannot access the address space commonly of a different application as well of the kernel, except there's some special mapping set up. This kernel can run on hardware directly, or they can run on a hypervisor, in which case it's a virtual machine. And then if you have hypervisors in deploy, then you can also have multiple operating systems running on the same hardware. In contrast to that, with unikernels, the application and the operating system is bundled in one image. We also commonly have hypervisor running under the hood, and this is usually the case because many of these unikernels won't support a wide range of hardware, whereas hypervisor environments are usually providing them with standardized devices, so they don't need to implement all kinds of hardware. There's also unikernels that can directly run on hardware, but these are more of the special cases. So what was the motivation behind creating these unikernels when we already had these traditional operating systems? So let's go back to the beginning of cloud computing. So in the beginning we had virtual machines, and here a virtual machine is something that emulates the hardware, and it can run an entire operating system along with the application. So the operating system doesn't need to be know that it runs on emulated hardware. And we can also then, this allows us to co-locate different operating systems, and we can provide strong isolation between them. So these operating systems can be from different parties, and one party cannot access the data from the other party. So far so good, but this isolation obviously also has come with some overhead, especially when we want to make these virtual machines fairly small, so it only runs a few applications, because every time we respawn a new virtual machine on hardware, then we need to give it space for the kernel as well as the virtualized hardware that we assign to each of these VMs. So they come with some overhead, also for boot time. So what people then came up with something called containers. They work a bit differently. So instead of having to provide virtualized hardware for each of these application runtimes, we can the application container only needs to contain the application as well as the services associated with that. And all containers share one kernel, and the kernel then provides isolation between these containers so that it's all implemented in software. While this is good for to reduce the overhead because we only have one kernel and no virtual hardware involved, it also comes with problems because each issue in the kernel can then lead to applications container being able to break out and potentially break into another container. So from an isolation perspective, security perspective, this is less than ideal, depending on the use case. So unikernels try to provide both strong isolation as well as a little operating system overhead. So what they do is by merging the application with the Unikernel runtime, they try to minimize the size and overhead of these applications. And then also as a result, we get really fast boot times. It also has some security advantages because these unique kernels only commonly include what's needed for this one application. Therefore, they can be smaller than traditional operating systems. However, there's still some issues with that approach because these unique kernels are still quite young, so there's a lot of tooling and ecosystem support that's still missing, which makes them challenging to adopt. So back to some unikernel concepts. So we already had it defined as like a special single address machine images that are constructed by using operating system library operating systems. So this is the definition as you can read it on unikernel.org. So specialized means here that each image will only have the OS services that are needed for the application instead of having an operating system that just implements all features and then the application chooses what features to use. It's a single address space. That means that there's only one process running, and if you need multiple applications, then yeah, you simply have multiple unikernels running side by side, for example, in virtual machines. And the library S here means that the application and the operating systems are run at the same privilege level. So commonly, if you do a system call, for example, if you try to read from a file, then you would perform something called an interrupt, where you would change from the normal application context into the operating system privilege level. And then the operating system would perform the system call in return. And with library OSS, this just becomes a simple library call, which is less overhead, but there's also less separation between the operating system and the application. So when to use unikernels, I want to go a little bit about advantages and disadvantages of that. As you've seen, unikernels provide a faster boot time than common operating system. They're more resource efficient because they provide less extensive features. They can also optimize the execution. For example, we saw that they can, for example, make system calls faster by having them only being a library system call. And they can also optimize for particular use cases. Having less code often means less attack surface, so it's improved security. And also, if we consistently put each process into its own unikernel, then we have stronger isolation as if we would, for example, co-locate multiple processes into the same virtual machine. Because the application and operating system is just one application image, we get something that is called immutable infrastructure, because when you, for example, push configuration changes, you would just rebuild the whole file system image and deploy the same thing as a whole. That in turn also can improve security because yeah, if an attacker cannot write to a file because there's no file to write to, then yeah, it's better security. Overall, unikernels are less complex than traditional operating systems. They can be deployed by just having one single image file that can be given to the hypervisor, which makes them easy to deploy, and they can often be also customized to the need by, for example, removing features that you don't need for this particular application. However, there's also some disadvantages of when using Unikernels. Many of these projects are not that old, and so the communities are also smaller, and it's hard to get support. There's also, when you have existing applications that you want to port to Unikernels, there's less operating system services that you commonly see. For example, let's say your application runs out of memory, there's less mature mechanism to just restart your application. The same with when you want to do performance monitoring, there are less APIs to do that. Unikernels itself are quite limited regarding to hardware support. And yeah, also platform support is less major. So you maybe see bugs that are already weed out with more traditional major operating systems. Because all of that, the learning curve is steeper than with normal operating systems. And you also have less interfaces to do things like debugging. The orchestration and existing orchestration and management tools that we see for applications, for example, in cloud environments, is often done in mind with um, normal operating systems, and for unikernels, they need to be fitted for the specific unikernel. Same for things like monitoring applications as well as logging. Unikernels are often optimized for a specific type of application, so there's no one size fit all. So you maybe have to choose different unikernels for different type of applications. And there's also some migration effort because the APIs of normal operating systems might be different from these unikernels, so they need to be adapted. Some of these disadvantages might also resolve itself as unikernel become a major, and Unicraft is one of the unikernels that try to address some of these problems. So what is Unicraft? It's a project that has entered the Linux Foundation, and its goal is to simplify building unikernels, and they have a modular approach that we will see in a bit. So the key objective is to make it easier to build unikernels, also to make them accessible to a wider range of developer. It's modular in the sense that you can include what you need. They try to stay quite compatible to the Linux kernel API. So if you have applications that run on Linux, they want to reduce the time it takes to port this to Unicraft. They also do some performance optimizations over what you've seen in other operating systems. So they have some benchmarks where they show that they can they can achieve quite high throughput for applications like key value stores because they can optimize on things like system calls, for instance, by just having less layers between the application and the hardware. They have quite good tooling that allows to customize your build and build images and test those. And their mainly focus is to provide a platform that can be used to deploy Unicraft images to cloud services. So, for example, web servers, DNS servers, network-based applications in general. So let's have a look at what this tooling looks like. So if you want to do a Hello World example, you start off with something called a graph file. So the graph file will specify what the project looks like, what libraries it uses, what platforms you want to run on, and what version. This is in the YAML format. Then there you have a make file which describes the build itself. So here we include one source file, the main.c, and this main.c looks fairly similar to what you usually have if you want to just do a Hello World application. And then once you have created all these files, we can run this tool called craft.build. And after it's finished building, we can say craft run. And this will run the application image that is built inside QEMU. And this QEMU has attached, will output all the output of the application to our terminal. So with this in mind, I want to get to the tasks that you have to solve regarding to Unicraft. So the first one is to get you more comfortable with Unikernels itself. To get you more comfortable with Unicraft itself. So you will learn a bit about x86 internals, an example find information about how rebooting works. So commonly system calls in operating systems are implemented as interrupts, whereas in Unicraft they're just function calls. And then Unicraft tries to implement all the system calls that also Linux provides, so they can be compatible with it. But it currently lacks the reboot system call, which is actually a fairly simple system call to implement. So your task is to implement that. And yeah, there's then some tests that will check if your virtual machine actually can reboot when using this system call. The second task is then, the more beefier and more complex task. So here you will address one of the problems that Unicraft has, and that is the debugger integration. So currently Unicraft has, to attach a debugger to Unicraft, what you have to do is using QEMU's own GDB integration. However, that has some downsides. It doesn't work, for example, if you have multi-core applications, or if you try to use a hypervisor that is not QEMU, or if you want to, for example, run on bare metal. So an alternative to this is having a GDB stub, which is a piece of web software that would run inside the Unikernel itself. So in this case, it's like independent on what the run hypervisor around this looks like. So your GDB would talk to this GDB stub running inside Unicraft, and they would talk over the console this remote protocol that GDB specifies. And this then is allows GDB to debug the application, with all the features that you can think of. So with that, you hopefully also get some insights about how debugger work. So the next time things are misbehaving, then maybe you have more insights. And with this last task in mind, I want to finish up my presentation. So to summarize, we learned today what unikernels are, what the advantages and disadvantages of unikernels are. We saw one example for unikernels called Unicraft, and I presented you the two tasks of this lab. One is implementing a new system call, and the second one is developing a GDB stub for Unicraft. Thank you for your attention, and with that, I'm gonna finish.